Have you ever wondered how your computer or smartphone performs complex tasks so efficiently? Well, the secret sauce to this magic is something called algorithms. Imagine an algorithm as a recipe, a step-by-step procedure, or a set of rules that guides the computer through solving problems, performing tasks, or accomplishing objectives. Algorithms are not just limited to the realm of computer science. They are fundamental components in various fields such as mathematics, data analysis, artificial intelligence, and even in our everyday life. From sorting your emails to providing driving directions, from predicting weather to processing your online transactions, algorithms are at work behind the scenes, making things smoother, quicker, and more efficient. So, whether we realize it or not, our daily lives are intertwined with these sets of rules, making complex tasks seem like child's play. In essence, algorithms are the brains behind the seemingly magical efficiency of our digital devices. Imagine needing to organize a pile of papers in alphabetical order. How would you go about it? Chances are, you'd use some form of sorting algorithm, even if you didn't realize it. Sorting algorithms are the unsung heroes of everyday life, arranging lists of items in a specific order, whether that's alphabetizing papers, arranging books on a shelf, or sorting a playlist by song title. Let's talk about a few types of sorting algorithms. First up, we have the bubble sort. Picture a group of people standing in a line, and you want to arrange them by height. You start at one end, comparing two people at a time. If the person on the left is taller, you swap their places. You keep going, swapping as necessary, until everyone is in order. That's bubble sort in action, stepping through the list, comparing adjacent elements, and swapping them if they're in the wrong order. Next, we have merge sort, which takes a divide and conquer approach. Imagine you have a deck of cards to sort. Instead of tackling the whole deck at once, you split it into smaller piles, sort those, and then merge them back together in order. This process is repeated until you have one sorted pile. That's the essence of merge sort, breaking down the task into manageable chunks, sorting them, and then merging them back together. Finally, let's look at quick sort, another divide and conquer algorithm. This time, let's say you're organizing books on a shelf. You pick a book, let's call it the pivot, and arrange the rest of the books so that all the ones with titles coming before the pivot in alphabetical order are on one side, and all the ones coming after are on the other. You then repeat the process with each of these two groups. That's quick sort. It's a line of people, a deck of cards, or a shelf of books. Sorting algorithms are working behind the scenes to bring order to our world. Ever lost a sock and had to rummage through your entire drawer to find it? That's a bit like how a computer uses a searching algorithm to find a specific item in a collection of items. But don't worry, it's not as chaotic as it sounds. Let's dive in. In the world of computing, searching algorithms are essential tools that help in locating a specific item among a collection. Imagine you have a drawer full of multicolored socks and you're searching for that one blue sock. How do you go about it? One way to do this is by using a linear search. This is the most straightforward searching algorithm. It starts at the beginning of your drawer and checks each sock one by one until it finds your blue sock, or it has checked all the socks. It doesn't require the socks to be in any particular order, which is handy if your sock drawer is as jumbled as mine. But what if your socks were neatly arranged in order of their colors? Could we search faster then? Enter binary search. This algorithm takes advantage of a sorted collection. It starts by checking the sock in the middle of your drawer. If that sock is not blue, but say green, it knows the blue sock must be in the half of the drawer with the cooler colors. It can then ignore the half with the warmer colors entirely. It then repeats this process, cutting the search area in half each time until it finds your blue sock or concludes it's not there. In essence, a linear search is like searching for a word in a book by starting at page 1 and reading every word until you find it. A binary search, on the other hand, would be like flipping to the middle of the dictionary, seeing whether the word you're looking for would be before or after that page, and then repeating the process until you find the word. So, just like you'd search for a lost sock, computers use searching algorithms to find specific items. Algorithms, in their many forms, are the unsung heroes behind our digital world, quietly powering the technology and processes that shape our everyday life. Think about finding the quickest route on a map. How would you do it? Well, in the world of computer science, we use something known as graph algorithms to solve this kind of problem. Graphs are structures that consist of nodes, which are the points or intersections on the map, and edges, which are the roads connecting these points. Now let's delve into some specific graph algorithms. First up, we have Dijkstra's algorithm, named after the Dutch computer scientist Edgar W. Dijkstra. This algorithm finds the shortest path between nodes in a weighted graph, where each edge has a certain cost or weight. Imagine you're planning a road trip and want to find the quickest route. Dijkstra's algorithm would take into consideration the distance of each road, the speed limits, and even the amount of traffic to determine the most efficient path for your journey. Next, we have depth-first search, or DFS for short. This algorithm explores as far as possible along each branch before backtracking. It's like venturing into a maze and following one path as far as it goes. If you hit a dead end, you backtrack and try another path. DFS is useful in situations where we want to visit every node in the graph, such as mapping a new area or navigating a complex network. Lastly, we have breadth-first search, also known as BFS. This algorithm explores all the neighbor nodes at the present depth before moving on to nodes at the next depth level. It's like dropping a stone in a pond and watching the ripples spread out evenly in all directions. BFS is used when we need to find the shortest path in an unweighted graph, where all edges have the same weight. These are just a few examples of graph algorithms, but they illustrate how these methods can help solve complex problems. They're used in a wide range of applications, from social network analysis to route planning in logistics and navigation systems. So much like finding the quickest route on a map, graph algorithms help find the most efficient paths in networks. Ever wondered how Netflix recommends shows you might like, or how your credit card information stays safe online? Well, these marvels of the digital age are brought to you by algorithms, specifically machine learning and encryption algorithms, respectively. Let's start with machine learning algorithms. These are designed to enable computers to learn from and make predictions or decisions based on data. For instance, consider linear regression. This algorithm establishes a relationship between dependent and independent variables by fitting a straight line to observed data. It's like trying to predict your score in a video game based on the number of hours you've played. Next, we have decision trees. These algorithms break down a dataset into smaller subsets based on different conditions, creating a tree-like model of decisions. Imagine you're deciding what to wear. The decision tree might ask, is it raining? If yes, wear a coat. If no, it might ask, is it above 70 degrees? If yes, wear shorts. If no, wear pants. You get the idea. Then there are neural networks, a set of algorithms modeled loosely after the human brain, designed to recognize patterns. They power things like speech recognition in your smart speaker, or face detection in your photo app. Moving on to encryption algorithms, these are crucial for protecting the confidentiality and integrity of data. Take the Advanced Encryption Standard, or AES. It's a symmetric encryption algorithm widely adopted for securing sensitive data. You can think of it like a secret code that only you and the intended recipient know, keeping your messages safe from prying eyes. Another common encryption algorithm is RSA, named after its creators Rivest, Shamir, and Adelman. It's an asymmetric encryption algorithm used for secure data transmission over insecure networks. Imagine sending a locked box through the mail. You send the box locked, and only the receiver has the key to open it. That's kind of how RSA works. So from recommending your next binge watch to keeping your online transactions secure, algorithms are working tirelessly behind the scenes. So, we've journeyed through the world of algorithms, but what does it all mean? Well, in essence, algorithms are the unsung heroes of our digital lives. They are the step-by-step procedures or sets of rules that solve problems, perform tasks, and accomplish objectives. We delved into sorting algorithms like bubble sort, merge sort, and quick sort, which arrange items into a particular order. We explored searching algorithms, such as linear search and binary search, that help locate specific items in a collection. We ventured into the realm of graph algorithms like Dijkstra's algorithm, depth-first search, and breadth-first search, which operate on graphs to solve complex problems. We also examined machine learning algorithms, including linear regression, decision trees, and neural networks, that enable computers to learn and make predictions. Lastly, we touched upon encryption algorithms, like AES and RSA, that protect our data's confidentiality and integrity. In the end, algorithms play a fundamental role in shaping our modern world, powering technologies and processes across various domains. Next time your device does something impressive, remember the humble algorithm at work?